Hello and welcome back to Unit 3 of Geometry at CHS with Abden, with your name here. Or maybe you got this packet. Yeah, we're having to mix and match some packets. I'll be jumping back and forth so you can see both of them. Let's see what we've got. The jumpstart is a notice and wonder. The following students have observed that the sum of two odd numbers seems to always be an even number. But their peers aren't convinced that this is always the case. Each student has given a different explanation as to why they think this claim is correct. This is L3.1. We made it. I heard one of my teachers say that the sum of two odd numbers is always even, and she knows everything about math. So this is called an appeal to authority, or knowledge from authority. It's considered weak knowledge because maybe your teacher's wrong. I tried a lot of examples and I found that the sum of two odd numbers is always even. For example, 3 plus 5 is 8, and 19 plus 21 is 40. So this is called knowledge from examples or evidence. Student number 3, I know that an odd number of objects can be paired together in groups of 2 with one object left over. Yeah, if it's odd, then you're always going to have one left over when you pair off by groups of 2. If I combine two such groups together, the extra ones from each group will also pair together. So the sum of two odd numbers will always be an even. I drew the following diagram to show what I was thinking. Okay, so this is called knowledge from reasoning. Reasoning, logic, and in this case a visual or diagram. Student 4, since an odd number is one more than an even number, I can represent odd numbers algebraically as 2 times some number plus 1. That'll always be odd. Whatever m is, if m is 5, 2 times 5 plus 1, that's 11. Or 2 times n plus 1, so n could be 6. 2 times 6 is 12 plus 1 is 13. So these are guaranteed odd makers. Okay, no matter what number you put in for m or n, it's going to make 2 odd numbers. But then, if they add these two algebraic representations together, 2m plus 1 plus 2n plus 1, they can drop the parentheses, since we can do that with the associative property, and there's no multiplier here. Or some people like to just multiply ones. Combine like terms, and then factor a 2 out. If you guys know about factoring, divide a 2 out to the front, and now it says 2 times something, and 2 times something is always even, no matter what this is. Doesn't matter what m and n and 1 is. When you double it, it becomes even. The last expression is even, since 2 times something, so the sum of two odd numbers is always even. So this is, again, knowledge based on reason, logic, symbolic representation, and we'll talk more about the types of knowledge as we go forward. Our learning focus today, examine ways of knowing that the sum of the angles in a triangle is 180 degrees. And also, how do you know something is true? Are there different ways that I know or accept things to be true? You may know that the sum of the interior angles of any triangle is 180 degrees. If you didn't know, you do now. But an important question to ask yourself is, how do I know that? We know a lot of things because we accept it on authority. We believe what other people tell us. Things such as the distance from the Earth to the Sun is 93 million miles, or that the population of the United States is growing about 1% each year. Other things are just defined to be so, such as the fact that there are 5,280 feet in a mile. Some things we accept as true based on experience or repeated experiments, such as the sun always rises in the east, or I get grounded every time I stay out after midnight. In mathematics, we have more formal ways of deciding if something is true. So in other words, all these examples, defining something to be true, observing something to be true, or being told that something is true, all of those are weak. In mathematics, we have a formal, strong system of proof. It's the strongest form of knowledge. That's why people love math so much and keep studying it into college, because they want to get a piece of that sweet, sweet truth. So experiment number 1, cut out several triangles of different sizes and shapes. We did this as a class yesterday. We all made triangles. We cut them apart with squiggly lines, and we rearranged them along a line, showing that all the angles made 180 degrees. Because everyone lined up the 3 angles into 180 degree line, this suggests all triangles have 180 degrees in their internal angles. Since you and your classmates have performed this experiment with several different triangles, does it guarantee that we will observe the same result for all triangles? Why or why not? It's weird. Like, obviously, once you see a bunch of examples and you never see a counterexample, you start to suspect it's definitely true. However, that's still weak. That's still not actually a logical argument that it always has to be true. And there's lots of examples where something seems to be true, there's never an opposite example, and then suddenly one comes along and ruins it. So we need, that never happens to an argument based on logic, unless there's a flaw in the logic. But that's what being a mathematician is about, is testing and making sure you find all the flaws in the logic. And if no one can find any flaws, then it's accepted as true, guaranteed. No. Many examples is not all possible examples. There are cases where, like, you can exhaust the options. So, like a Rubik's Cube. Even though there's billions of ways to solve a real Rubik's Cube, it's not unlimited. And so people have done what's called a brute force attack, where they just try all the combinations. And if you try every combination, actually examples is proof, because you've tried them all. But there's an infinite number of triangles, so we can't do that on triangles. Perhaps a different experiment will be more convincing. Cut out another triangle and trace it onto a piece of paper. It will be helpful to color code each vertex angle of the original triangle with a different color. As new images of the triangle are produced during this experiment, color code the corresponding angles with the same colors. We didn't do that, but we did make this diagram. Locate the midpoints of each side of your cutout triangle by folding the vertices. Oh, that was cool. Rotate your triangle. We could have done that. We just rotated it. We rotated it 180 degrees. Remember doing that? About the midpoint. But then once we rotated it, we would just cheat and line it back up. And then we traced the new triangle. So we were making this. We would make this sort of thing. I have one right here I can show you. This is what we ended up making. Well, the only thing we didn't do was color them in. But we used numbers, because we're cool. What does this experiment reveal about the sum of materials that you cut out? Well, right here, 1, 2, 3, all 3 angles are together, and they're along a straight line. So it's similar to the one where you rip the corners off and line them up. Suggests 180 degrees. Suggests 100 degrees in a triangle. Always. Now this is closer to a proof, because you could work out that logically, no matter what triangle you're using, rotating around the midpoints will create a situation where they line up like this. However, that proof is going to be technical and long and drawn out, and maybe is beyond the scope of us right now. So let's see what else we can do. Do you think you can rotate all triangles in the same way about the midpoints of its sides and get the same results? Yeah, 'cause that's what they're kind of getting at. Yes. By logic of midpoints and rotations. Now, we could maybe lay this out. It would take a while. We'd have to say, we'd have to talk about midpoints and how and rotate 180 degrees, line back up, balance. We could bring it together. This is closer to an actual mathematical proof. All right. Experiment number 2 produces a sequence of triangles as illustrated in the diagrams. Yeah, we did this. Rotating around this point. Spins around, makes that. Finally, we end up with this. If you're in this booklet, it's cool.